Good morning to all of you. Now we discuss about the chapter of inorganic chemistry. The name of the chapter is Chemistry of Noble Gases. Group 18 of the periodic table consists of 6 elements: helium, neon, argon, krypton, xenon, and radon. This is a unique group of all its members are gases at ordinary temperature and pressure. Prior to 1962, the elements of this group were known as inert or rare gases. Today, both the names have been proved wrong. This is because these gases are no more rare now, as these are found in the atmosphere, although only argon is present in high proportion. Some of these gases, especially xenon and radon, have been found to be reactive, and accordingly we can no longer call them as inert gases. These gases have been correctly named now as noble gases in view of their reluctance to react with everything. In fact, the noble gases make up the least reactive group in the periodic table. Position of noble gases in the periodic table. Mendeleev arranged all the known elements in form of table known as periodic table in 1869 on the basis of physical and chemical properties of the element. The noble gases were not known at that time. As a result, no place could be allocated to these gases. Later on, when these gases were discovered and characterized, it was thought to position these gases in the periodic table on the basis of their physical and chemical properties. It is curious to note that these gases are not reactive at all. On the basis of their atomic mass and non-reactive nature, Ramsay proposed altogether a new group called zero group for these gases. The group O suggests extreme inactivity or zero valency of the noble gases. Prior to the discovery of noble gases, the elements happened to be arranged in a manner that all the electropositive elements were placed on the extreme left of the periodic table and the electronegative elements on the extreme right of the periodic table. Thus, one can sense a very sudden change in the properties from the most electronegative halogen to the most electropositive alkali metals. Now, the inclusion of these gases in between the halogens and the alkali metals appears justified, as these gases have neither electronegative nor electropositive character. The position of these gases was finally confirmed by Moseley, who suggested atomic number as the basis of classification of elements in the modern periodic table. These gases now happily enjoy the last column on the extreme right of the long form of the periodic table. The discovery of the noble gases. Helium was detected for the first time in the spectrum of the Sun in 1868, hence its name derived from Greek helios for sun. It was nearly 30 years later when Ramsay found helium as a gas given off from a radioactive uranium source. The discovery of argon was made by Lord Rayleigh by measuring carefully the density of nitrogen samples from different sources. He observed that the nitrogen samples from air was always denser than that obtained from the decomposition of ammonia. It is interesting to note that when Ramsay burned magnesium in nitrogen from air, he found a small amount of the gas which was identical to that found by Rayleigh. He named this gas as argon. It comes from the Greek argos for the ideal one. The other three gases were obtained by the fractional distillation of liquid air and were named neon, the new one, krypton, the hidden one, and xenon, the stranger. The name radon comes from its radioactivity. William Ramsay and Lord Rayleigh were the main contributors for the discovery of inert gases, and both of them were decorated with the Nobel Prize in 1904. Electronic configuration. The electronic configuration of all the elements of the noble gases is presented in the table, like helium, symbol He, atomic number 2, electronic configuration 1s2. Neon, symbol Ne, atomic number 10, electronic configuration 1s2, 2s2, 2p6. Argon, symbol Ar, atomic number 18, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. Krypton, symbol Kr, atomic number 36, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6. Xenon, symbol Xe, atomic number 54, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 5p6. Radon, symbol Rn, atomic number 86, electronic configuration 6s2 and 6p6. Helium is first element of the noble gases, has the electronic configuration 1s2, whereas all the other elements have the general electronic configuration ns2 and p6, where n is the period number. Thus all the noble gases with the exception of helium, have 8 electrons in the valence shell. Physical properties. All the elements of noble gases are placed in group 18 of the periodic table. It is a unique group where all the members are colorless, odorless, and monoatomic gases at room temperature. The monoatomic state of these gases is due to the stable electronic configuration of their atoms. All these gases occur in the atmosphere. It is interesting to note that the total volume of the noble gases come close to 1 by 1/20th of the volume of the air. These gases neither burn nor support combustion. In fact, these gases constitute the least reactive group in the periodic table. First, atomic radii. The atomic radii of noble gases increase from helium to xenon as one moves from top to bottom in a group. This is because on moving from one atom to another in a group, there is an increase in the principal quantum number. As a result, new shells are being added and the electron cloud expands. The atoms of noble gases are held together by van der Waals forces. The forces are very weak. To give you an idea, let us consider the bond energies of a normal ionic or covalent bond compared to the bond energies in a system where van der Waals forces are operative. The bond energies in the former varies from 100 to 500 kJ per mole, whereas in the latter case it varies from 5 to 50 kJ per mole. The atoms of the noble gases are held together at longer distances. It is therefore important to mention that in case of noble gases, one should talk of van der Waals radii rather than covalent radii. This is because noble gases do not form covalent bond but are held together by van der Waals forces. Second, ionization energies. The first ionization energies of the noble gases are very high. This is primarily because of the completely filled electronic configuration. However, within the group, the ionization energies decrease down the group from helium to radon because of the increase in atomic radii. Third is electron affinities. The electron affinity of noble gases are nearly zero because of their stable electronic configuration. It is clearly suggests that the noble gases have no tendency to accept electrons. Fourth, melting and boiling point. The melting and boiling point of noble gases are very low. This is because the atoms of these elements are held together by weak van der Waals force of attraction both in the liquid as well as in the solid state. An inspection of the table reveals that down the group from helium to Rn, the melting and boiling point of these elements show a regular increase due to corresponding increase in the magnitude of their van der Waals forces with the increase in the size of the atom. Fifth, solubility in water. The noble gases are slightly soluble in water. The solubility has been found to increase down the group from helium to radon. Sixth, ease of liquefaction. The noble gases are not easily liquefied. The ease of liquefaction of a gas depends upon the magnitude of attractive forces present in the atoms or molecules. Since these gases are held together by weak van der Waals forces, these cannot be easily liquefied. However, as the atomic size increases, the magnitude of the van der Waals force also increase, and thus the ease of liquefaction increase as one move down the group from helium to radon. Chemical properties of the noble gas. After the discovery of noble gases, many attempts were made to prepare compounds of these elements. However, all attempts before 1962 were unsuccessful and the elements were compelled to be known as inert gases. The inertness of these elements to chemical reactivity is attributed to: first, the state-closed shell electronic configuration NS2-NP6 of all noble gases excepting helium, which has the electronic configuration 1s2. Second, the high first ionization energies of noble gases. Third, nearly zero electron affinities of noble gases. On the basis of above facts, noble gases do not have any tendency to lose, gain, or share electrons with other atoms. The first compound of the noble gases were prepared by British born Canadian chemist Neil Bartlett in 1962. In fact, Bartlett was studying the reaction of platinum 6 fluoride PTF6, which is a red crystalline solid. He observed that when PTF6 is exposed to molecular oxygen, a yellow ionic solid of composition O2 positive PTF6 negative is formed. The above reaction clearly demonstrates that oxygen has been oxidized to O2 positive, thus suggests the high oxidizing character of platinum 6 fluoride. While teaching a first year chemistry class, Bartlett noticed that the first ionization energy of xenon gas was almost identical to that of the dioxygen molecule. This made Bartlett to think that PTF6 can remove an electron from O2. It should be able to remove electron from the xenon atom. He therefore predicted the reaction between xenon and platinum 6 fluoride to form xenon positive and PTF6 negative. Bartlett carried out the reaction and found that gases xenon react with the red vapors of PTF6 to give a yellow solid of composition ZXe positive, PTF6 negative. This marked the first preparation of the compound of group 18, breaking the old myth that these elements are inert. Bartlett, this discovery opened a new field of chemistry, and within months, scientists prepared fluorides of xenon, namely xenon fluoride and xenon Fe2 and ZXeF4. Among the noble gases, xenon is known to form the maximum number of compounds, whereas krypton forms only a small number of compounds. Before we discuss the chemistry of noble gases, it is important to answer some curious questions, which are: first, what are the factors that are responsible for the late discovery of compounds of these gases? Second, why does xenon form the maximum number of compounds with fluoride and oxygen? Late discovery of compounds of noble gases. Before 1962, it was believed that the noble gases were not reactive at all. This was attributed to the high first ionization potential and nearly zero electron affinity of the gases. All attempts to prepare the compounds of these gases were not met with success. It is interesting to note that William Ramsay sent a sample of argon to the French chemist Henri Moissan to see whether argon reacted with fluorine. Moissan found that there was no reaction between fluorine and argon. This led Ramsay to conclude that the noble gases are chemically inert. On the basis of chemical inertness of noble gases, Lewis in 1960 formulated the important rule we today call it as the octet rule. According to this rule, when an atom forms a compound, it either gains, loses, or shares electron to obtain 8 electrons in its valence shell. You should remember that octet refers to a valence shell containing 8 electrons. Compound of xenon. The historical reaction of xenon gas with platinum 6 fluoride marks the first chemical compound of xenon. If you recall, Niels Bartlett discovered this reaction in the year 1962. The xenon was credited the first and foremost element of the noble gas to open a new field of chemistry called the chemistry of noble gases. Today we have a very rich and interesting chemistry of xenon compounds with highly electronegative elements or groups containing highly electronegative elements in addition to some compounds of krypton. Of all the electronegative elements, non-fluorine is most electronegative. It is able to stabilize the highly oxidizing noble gas compounds. Now we are all set to discuss the chemistry and important properties of compounds of xenon in particular and noble gases in general. Xenon second compounds. A. Xenon difluoride XeF2. First preparation. It can be prepared by the following methods. First, xenon difluoride is best prepared in the laboratory by heating xenon and fluorine in the molar ratio 2:1 at 400 degrees Celsius. Xenon is always taken in excess to avoid the formation of xenon tetrafluoride. Second, it can be prepared by subjecting a mixture of xenon and fluorine in the molar ratio 2:1 to electric discharge. Third, it can be prepared in quantitative yield by reacting xenon with oxygen monofluoride or 2F2 at low temperature in a nickel or monel vessel. Properties: xenon difluoride is a colorless crystalline solid which melts sharp at 129 degrees Celsius. Second, it dissolves completely in anhydrous hydrogen fluoride without any reason. Third, it gets reduced to xenon with hydrogen. Fourth, it is soluble in water but undergoes show hydrolysis to produce xenon gas. Fifth, it gives substitution reaction with strong protonic acid HY. Sixth, it reacts with sulfur trioxide to give xenon. Seventh, xenon difluoride is a very clean fluorinating agent. It fluorinates double bond in organic compounds. Eighth, it is a strong oxidizing agent. It reacts with iodine in the presence of fluoride ion acceptor to give IF. Ninth, it reacts with covalent pentafluoride such as antimony fifth fluoride, arsenic fifth fluoride to form two types of solid compound in which xenon difluoride acts as a fluoride ion donor. For example, when the reaction is carried out in 1:1 molar ratio as a 1:1 compound is formed. These compounds XeF2.MF5 have been established to contain ionic species XeF positive, MF6 negative, where M is equal to P, AS or SB. Similarly, when the reaction is carried out in 1:2 molar ratio, a compound of composition XeF2.2MF5 is formed. The compound XeF2.2SbF5 has been shown to contain XCF positive and Sb2F11 negative ions. The ion XCF positive is strongly bonded to Sb2F11 negative through a fluorine bridging as shown in figure. Xenon difluoride have also been shown to react in the 2:1 molar ratio. The compound 2XeF2.AsF5 is conceptually equivalent to Xe2F3 positive AsF6 negative. The ion Xe2F3 positive has the expected linear geometry around xenon and an angular symmetry at the center fluorine atom. 10th, xenon difluoride in anhydrous hydrogen fluoride reacts readily with platinum metal and sulfur powder and iridium to produce the highest fluoride according as platinum plus xenon fluoride in presence of HF, PTF6 and ZXe. Shape and structure of xenon fluoride, that is XeF2. On the basis of infrared and Raman spectroscopy, the geometry of xenon difluoride have been estimated to be linear. The symmetry of xenon difluoride can also be explained on the basis of valence bond theory. The valence electronic configuration of xenon in the group state is 5s2 5p6. Upon excitation, one of the 5p electrons is promoted to 5d orbital that results in two unpaired electrons, one in 5p and the other in 5d orbital. Now one 5s 3 5p and one 5d orbitals hybridize to give 5sp3d, one hybridized orbitals that are directed to adapt trigonal bipyramidal geometry. The two orbitals which are singly occupied are used by two fluorine atoms to form two xenon fluoride bonds, whereas the other three orbitals contain electron pairs. The two xenon fluoride bonds lie in a straight line while the three lone pairs of electrons occupy the equatorial position. The xenon difluoride possesses the linear symmetry. Xenon fourth compounds, that is xenon tetrafluoride, XeF4. Preparation: it can be conventionally prepared by heating a mixture of xenon and fluorine in the molar ratio 1:5 at 400 degrees Celsius under a pressure of 5 to 6 atmosphere. The reaction is ideally conducted in a nickel container. Xe plus F2 in presence of 400 degrees Celsius 566 atm pressure converted to XeF4. Xenon tetrafluoride can also be prepared cleanly by passing an electric discharge through a mixture of xenon and fluorine in the molar ratio 1:2 at low temperature and low pressure. Properties: first, it is colorless crystalline solid with melting point 117 degrees Celsius. Second, it is quantitatively reduced by hydrogen gas. Third, it is a strong oxidizing agent. It oxidizes potassium iodide to iodine. Fourth, it is a stronger fluorinating agent than xenon difluoride. It can fluorinate both elements and compounds. Fifth, it reacts with boron trichloride to form boron trifluoride. Sixth, it is readily hydrolyzed by water giving xenon trioxide, that is XCO3. However, if the reaction is carried out at -80 degrees Celsius, it results in the formation of xenon oxyfluoride. Seventh, it readily forms addition compound with pentafluoride of phosphorus, arsenic and antimony of composition XCF2.MF5 and XCF2.2MF5. XeF3 positive ion has T-shaped trigonal bipyramidal structure as shown. Structure and bonding of XeF4, that is xenon tetrafluoride. Spectroscopic studies have shown that xenon tetrafluoride has a square planar structure. The valence bond description of XeF4 can be easily explained on the basis of electronic configuration of xenon atom. Xenon atom in the ground state has 5s2 5p6 in the outer electronic configuration. On excitation, two of the 5p electrons are promoted to 5d orbital so that there are 4 unpaired electrons as shown in the figure. A total of 6 orbitals intermix to give 6 sp3d2 hybridized orbitals. These orbitals are directed towards the corners of an octahedral. 4 of the hybrid orbitals containing single electron overlap with the 2p orbitals of fluorine to form 4xef sigma bond. The other two positions are occupied by the lone pairs. Xenon oxyfluoride XeOF2. Preparation: xenon oxyfluoride is prepared by the partial hydrolysis of xenon 4 fluoride at -80 degrees Celsius. The structure of this molecule is T-shaped as shown below. The structure can also be explained on the basis of valence bond theory. The outer ground state electronic configuration of xenon is 5s2 5p6. In order to account for the bonding, two of the 5p electrons are promoted to the vacant 5d orbitals. In this case, 5 orbitals intermix to give 5sp3d1 hybridized orbitals. It is important to note only one singly filled 5d orbital is left unhybridized for pi bonding. Three of the singly filled 5 hybrid orbitals overlap with 2 fluorine and 1 oxygen atom to form 3 sigma bonds via 2 XEF and 1 XEO bond. One of the unhybridized 5d orbital is used in forming an additional bond with oxygen by sidewise overlapping, that is a pi bond. Thus, in XeOF2 there is a double bond between xenon and oxygen in addition to two XeF single bonds. There are two lone pairs of electrons on xenon atom. Because of the presence of lone pair of electrons, there is a mutual repulsion between the bonding and non-bonding pair of electrons, and consequently there is distortion in the geometry. Thus, XeOF2 acquires a T-shaped structure. Xenon hexafluoride XeF6 preparation. It is best prepared by heating xenon gas with a large excess of fluorine in the ratio 1:20 at 300 degrees Celsius under 50 atmospheric pressure in a nickel vessel. It can also be prepared by the reaction of XeF4 with O2F2 at low temperature, that is -120 degrees Celsius. Properties: it is a colorless solid with melting point 49.5 degrees Celsius. Second, it is the most volatile of all the fluorides of xenon. In the vapor state, it has greenish yellow color. Third, it reacts readily with water to form xenon trioxide, which is a powerful explosive. Fourth, it is extremely reactive towards glass or quartz and produces the dangerously explosive xenon trioxide. This is the reason that the preparation of XeF6 is always carried out in a nickel vessel. Fifth, it reacts with the pentafluoride of phosphorus, arsenic, antimony, and platinum and forms stable compounds. The XeF5 positive in these compounds have been shown to have square pyramidal geometry. It reacts with alkali metal fluoride to form heptafluorohexenates. Alkali metal fluoride are well-known fluoride ion donors. On heating, heptafluorohexenates decompose to give stable octafluorohexenates as XeF82 negative has a square anti-prismatic structure. Seventh, it is reduced to xenon upon reaction with hydrogen, ammonia, and hydrogen fluoride. Shape and structure of XeF6. The valence bond description of XeF6 can be explained by considering the electronic configuration of xenon atom. The ground state outer electronic configuration of xenon is 5s2 5p6. On excitation, 3 of the 5p electrons are promoted to vacant 5d orbitals, so that there are 6 unpaired electrons available, 3 in the 5p orbitals and 3 in the 5d orbitals. Thus, a total of 7 orbitals hybridized to produce 7 sp3d3 hybrid orbitals. 6 of the singly occupied orbitals are used for bonding with 6 fluorine atoms. The 7th orbital contains a lone pair. The distribution of 7 hybridized orbitals should give a pentagonal bipyramidal geometry. However, XeF6 molecules has distorted octahedral structure. This can be explained if all the 6 positions are occupied by the fluorine atom and the lone pair is present at the center of one of the 6 triangular faces. This type of octahedron is called a capped octahedron. Xenon oxytetrafluoride XeOF4 preparation. It can be prepared by the partial hydrolysis of xenon hexafluoride. Second, it can also be prepared by the controlled reaction of xenon hexafluoride with silicon dioxide at low temperature. Third, it can be conventionally prepared by heating a mixture of xenon and fluorine in the molar ratio 1:4 in the presence of excess of oxygen. Properties: first, it is a colorless compound with melting point -46 degrees Celsius. Second, it reacts with water to form xenon dioxide difluoride, which further reacts with water to give xenon trioxide. Third, it is reduced by hydrogen gas to form xenon. Structure and bonding. Xenon atom has the outer electronic configuration 5s2 5p6. In order to justify the bonding around xenon in XeOF4, electrons sitting in p orbitals have to be promoted to vacant 3d orbitals as shown in figure. 1 5s 3 5p and 2 5d orbitals intermix to form 6 sp3d2 hybrid orbitals, which are directed towards the corners of an octahedral. One of the 5d orbitals remain unhybridized. In the formation of XeOF4, 5 of the singly filled hybrid orbitals of xenon overlap with the singly filled orbitals of 4 fluorine atom and 1 oxygen atom to form 4 XeF single bonds and 1 XeO single bond. The unhybridized 5d orbitals of xenon forms a pi bond with the oxygen atom. Thus, the single XeO bond becomes Xe double bond O double bond and the molecule acquires a square pyramidal structure. Xenon dioxide difluoride XeO2F2. It is prepared by mixing xenon trioxide with xenon oxytetrafluoride at low temperature. XeO3 plus XeOF4 converted to XeO2F2. It can also be prepared when xenon oxytetrafluoride is either hydrolyzed with water or made to react with silica. Properties: first, it is a colorless solid. Second, it melts at 30.6 degrees Celsius. Third, it gets easily hydrolyzed with water to give xenon trioxide. Structure and bonding. The valence bond structure suggests trigonal bipyramidal geometry with one equatorial position occupied by a lone pair of electrons as shown in figure. The bonding can be explained as discussed in the case of xenon oxidifluoride. Xenon trioxide XeO3. Preparation: xenon trioxide can be prepared by the complete hydrolysis of either xenon 4 fluoride or xenon 6 fluoride. During experiments on xenon hexafluoride, several explosions have occurred because of the hydrolysis of XeF6 to xenon trioxide. The reaction can be controlled by carrying out the reaction at low temperature, wherein the hydrolysis proceeds stepwise. As properties: xenon trioxide is a white non-volatile solid. Second, it dissolves readily in water but explodes violently in the dry state. It is therefore advised to keep it in dissolved form. Third, it is not ionized in solution and concentration as high as 4 m can be prepared. Fourth, in alkaline solution, it behaves as a weak acid and exists as a xenate ion HXeOFO4 negative, from which sodium salts can be precipitated as NaHXeO4 1.5H2O. The aqueous xenate ion slowly disproportionates to perxenate and xenon gas. Fifth, it is one of the strongest oxidizing agents known in aqueous medium. It is oxidizing reaction. Xenon trioxide releases xenon gas. It reacts with potassium iodide and liberates 3 moles of iodine per mole of xenon trioxide. Sixth, it reacts with XeF6 and XeOF4 as structure and shape of xenon trioxide. The outer electronic configuration of xenon is 5s2 5p6, which has no unpaired electrons. In the formation of xenon trioxide, it is anticipated to have 6 unpaired electrons on xenon atom. This could be accomplished by exciting 3 of the 5p electrons to the higher vacant 5d orbitals, as shown. On 1 5s and 3 5p orbitals hybridize to form 4 sp3 hybrid orbitals, which are directed towards the four corners of tetrahedron. One can see that there are 3 electrons on xenon that remains unhybridized. 3 of the 4 hybridized orbitals, which are singly occupied, overlap with one of the singly filled the 2p orbitals of oxygen and form 3 sigma bonds. The 3 unhybridized orbitals of xenon overlap sidewise with the 2p orbital of 3 oxygen and form a double bond. It is important to note that one of the hybrid orbitals contains a lone pair of electrons. As a result, the molecule has a pyramidal geometry in place of tetrahedron. Xenon tetraoxide. Sodium perxenate NaXeO3 when treated with concentrated sulfuric acid gives xenon tetraoxide XeO4. It is a yellow, volatile, highly unstable solid. It decomposes explosively in the solid state even at temperature as low as -40 degrees Celsius. Compounds of other noble gases. Of all the noble gases, it is chemistry of xenon that has been studied in detail because of its reactivity towards highly electronegative element, namely fluorine. It is only recently that krypton and radon have been shown to react with fluorine to yield KrF2, that is krypton difluoride, and krypton tetrafluoride and radon difluoride. Krypton difluoride deserves special mention. It can be prepared by reacting krypton with fluorine at low temperature in the presence of gamma rays. It is a colorless solid and gets easily hydrolyzed. It has been found to be a clean fluorinating agent. The structure of krypton difluoride has been shown to be linear, which can be easily explained on the basis of sp3d1 hybridization. RNF2 has been prepared, but it is highly unstable. No compound of helium and neon has been prepared so far. This is primarily because of their very high ionization potentials compared to xenon and krypton. In addition, there are no vacant d orbitals in helium and neon, where the s and p orbitals of these gases can be promoted favorably. Clathrates compounds. Clathrates are compounds in which atoms or molecules of one substances are trapped within the cavities of crystal lattices of others. It is important to note that rare gases, now noble gases, were the first to be trapped and form clathrate compounds. Normal chemical compounds have ionic or covalent bonds. However, in clathrates, atoms or molecules of the appropriate size are trapped in the crystal lattice of other compounds. Also, the gases are trapped; they do not form bonds. Clathrates are also known as case or enclosure compounds. In these compounds, one of the component has an open structure in the crystalline state containing holes or cavities in which the other component is trapped. Thus, if an aqueous solution of quinol is crystallized under a pressure of 10 to 40 atmosphere of argon, krypton or xenon, the gas becomes trapped in the cavities of organic molecules. The crystal structure with cavity is called the host and the gaseous atom entrapped in it is called the guest. The crystals are quite stable and can persist for several years without decomposition. However, when the clathrate is dissolved, the hydrogen bonded arrangement of beta-quinol breaks down, the noble gas escapes. Even the clathrate decomposes on heating with the escape of trapped noble gas. X-ray study shows that somewhat spherical cage of about 4 angstrom diameter is formed by 3 quinol molecule being bound with hydrogen bonds as shown below. Thus, the ratio of quinol to entrapped atom is usually 3:1. The three gases argon, krypton, and xenon all fit into the quinol structure. The argon compound has the approximate composition. It is a stable crystalline solid with a very small argon pressure at room temperature. Helium and neon do not give clathrate compounds since their small size do not permit the inert gas to fit into the case. Noble gases, with the exception of helium and neon, form also clathrate compound if water is crystallized slowly in the presence of noble gases. The maximum composition formula of such clathrates in H2O Mng, where Ng is the noble gas. The value of N has been found to be 46 while that of mass M has been found to be 8. The ratio of 46:8 is very close to the experimental ratio of 8H2O:1 Ng. And these clathrates compounds are commonly called the noble gas hydrates. The heavier noble gases have also been trapped in the cavities of synthetic zeolates. Clathrate compounds find extensive uses in many applications. Some of these are: first, the noble gases can be separated by forming the clathrates. If you recall, helium and neon do not form clathrate when quinol is crystallized from its solution in the presence of mixture of noble gases. This way, the heavier noble gases can be separated from helium and neon. Second, the most important use of clathrate is that this provides a very convenient means of storing the radioactive isotope of krypton and xenon produced in nuclear reactors. Third, krypton 85 in the form of clathrates may be used as a source of energy for small atomic batteries. Fourth, krypton 85 clathrate provides a convenient and useful source of beta radioactive. Fifth, clathrate compounds are convenient storage of inert gas. Thank you.